Okay, welcome everybody to this new session of the Senior Seminar course. Today, we're pleased to have with us Professor Lohner, who is going to talk us about the high-fidelity simulation of pathogen propagation, transmission, and mitigation. Um, Reynal is the head of the CFD Center of George Mason University in Virginia, and he has been working mainly on numerical method solvers, regeneration, parallel computing, for fluid structure interaction, shape and process optimization, and computational crowd dynamics. I hope that this will be a very interesting and hot topic for today's situation. We must say that today we have a special seminar because differently to what we have in the previous months, we are in a blended session. So we have part of the audience are here in the CNET Synthesis room. We have almost 10 people here, apart from all of you who are connected from outside. So I hope that it goes very well, as always. And Reino, one.
Okay, thank you very much. It's a great pleasure to be back in Barcelona after last year's impossibility of coming here. As perhaps many of you know, I very much like to come here and to work here in the summer. Maybe we can close that window. So the topic of my talk is has to do with COVID-19. So before I start, I'd like to acknowledge everybody that has contributed to this work. First of all, the people in my CFD center, then the people in the math department of GMU. We've also had some input from the Center for Human and Health Services at the George Mason University, which is a fairly large establishment. Then some colleagues from ASI and from CIMLI here. And then also some contributors from the New York Times, from the US District Courts of New York and Maryland, and from the Deutsche Bahn. This is an outline of what I'd like to cover. It's a fairly ambitious agenda, and I hope I get through it in 1 hour. So let's start with the background. Imagine that you're fishing in Argentina, and you're blissfully unaware of what's happening around the world. And when you return to your parents' farm, then you find out that the borders are closed. Okay, why are the borders closed? Because COVID is around, there are no flights back. And so you have time to ask questions because you have a lot of time suddenly. And so the crucial question is, what can CFD or what can computational sciences contribute to the crisis that was mounting? So there were two main topics there. One was to identify and to elucidate the transmission mechanisms of COVID-19. And the second one was teaching and outreach to try to make people more aware of the possible dangers of certain behaviors. I got out via Brazil, the last but one flight. If I had missed that flight, there was one more flight and that was it. I would have been in Argentina for 6 months. So let's talk about pathogen transmission. One of the main avenues is sneezing, and you can see here a typical sneeze experimental picture. You can see there are two types of transmissions here that you can identify immediately. One is the one with small droplets. They travel as a cloud through the air. Think of it as smoke. And then you have the large droplets that travel ballistically through the air and fall down. Think of it as spitting. Then there is the breathing mode. This is the part that you cannot see, but still, when we breathe out and we are infected, we breathe out pathogens. You can see that those will move as air, and because our exhalation has a higher temperature, they will tend to go upwards in a quiet situation. And then there is finally the situation when you have HVACs or inflows like in this room here, and you have people moving. HVACs, typically the flow that is comfortable for humans is of the order of 0.2 to 0.3 meters per second. We tend to move between 1 and 1.3 meters per second. So clearly you're building wakes, and those wakes will enhance the transmission or the possibility of transmission of pathogens. So pathogens, in particular viruses, enter the body through the nose, mouth, or eyes and exit the body through the nose and the mouth. And you could sort of build a sequence of what is worse than the next one. So sneezing It's about 10 times more viral matter in the air than coughing, and that's about 10 times more than shouting, and it's about 10 times more than singing, and that's 10 times more than speaking. Okay, so you can build sort of a hierarchy of what is bad. Okay, and you have the main transmission modes, person to person. So this could be either large or small droplets, depending on the distance that these people are. Person, air, person. So you exhale into the air, that aerosol stays there or moves around, and then it's inhaled by another person. And then person, surface, person. So this would be a large droplet that is, say you're in an airplane, somebody sneezes, it falls on a seat, you're moving through the corridor, you put your hand on that seat, and then you put your hand in your mouth, or you rub your eyes, or whatever it is. The droplet distribution when coughing or sneezing has been studied extensively experimentally. This is a picture here from a paper from 1967. You can see here that we have particles on the order of 1 millimeter, a few of them. Of course, these are very large particles if you think about the volume and the content of viral matter compared to the smaller ones, because everything goes with the cube of the diameter. But you can see that we have quite a few on the order of 0.1 millimeter, and then we have quite a substantial amount also on the order of 10 to the minus 6 millimeters. And so if you remember 0.1, 0.01, 0.001 millimeters, then you can come up with the idea, well, how long will these particles take to fall to the ground? Or how long will they stay in the air? And you can come up with the final sink velocity of a particle in quiet air. And you can see that this is a simple analytical formula. It's the Stokes limit. You can see that anything that is below 0.1 millimeters basically stays in the air forever. Yeah. I mean, you have sink velocities of 10 to the minus 5. Okay, so it takes 100,000 seconds for this thing to move 1 meter down. Okay, so it's basically there forever. Now, the other thing that happens with particles is that they evaporate in air, particularly the smaller ones. The smaller, the faster. And what happens to the viral matter is that our saliva or our mucus builds like a gelatin around it. So that's why these are very small particles, but the viral matter stays alive, stays active, it doesn't get destroyed. So you can build the so-called Wells curve, and you can ask yourself, what happens first? Does the particle get to the ground, or does it evaporate first? Okay, and so here you have the two competing parts coming together. So this is time here, and this is the droplet diameter. And so this would be the time it takes to reach the ground, and this is the time it takes to evaporate. So you can see that anything below about 100 micrometers is basically evaporating. So that stays in the air forever. Because as you evaporate, the particle becomes smaller and smaller, so your diameter almost vanishes. Then, yeah, please.
Yeah, are there substantial differences between the evaporation rate of this mucus or water?
No. So you have a lot of water there, and what happens is that as it evaporates, the mucus shrinks and gets around the viral matter, and that's what stays in the air.
But if the water evaporates, then you can assume that it's destroyed.
Yeah. Water's out there. Yeah. So the question now is how much of an infectious dose, if you're going to make a transmission model, or if you're going to try to predict how many people are going to get infected, the question is how much of this viral matter is needed before a person gets really infected. Okay, and of course that's biology, so you have a huge variability in this. So it depends on your state of an immune system. You have weaker individuals and stronger individuals, your history of previous diseases that you had, the timing of the viral entry. So it's all coming in one swoop, or is it coming part by part? And then, of course, also your state of mucus and hair is it amenable or not? So that depends also on your current situation. We have data from biological warfare agents. You can imagine that if you're doing chemical warfare, or biological warfare, this has been researched. So you see that in some cases, you only need 10 bacteria to make it happen. That's all it takes, okay? And if you look at tuberculosis, 1 is enough, okay? So if you get that 1 bacterium into your nose or through the eyes or whatever, you're infected. COVID-19, it's about 100 to 200 so-called virals. These are viruses that are still active, that can still start reproducing, okay? So it's not a very high number, because you can have in a droplet, you can have thousands of these. And then the final question is, if you're going to make a transmission model, what is the lifetime outside the body? So we know that in air, these viral matter can stay alive or active for 1 to 2 hours. On some surfaces, up to 1 to 2 days. So of course, it depends on how much UV radiation you have, humidity matters and things like that. But from between 1 and 2 hours in air to 1 to 2 days on surfaces. Now, what is so bad about COVID-19? What is so bad about COVID-19 compared to other diseases is that the highest infectivity rate occurs 1 to 2 days before the symptoms occur. So that's why you have these gigantic numbers of transmission, because the person that has it doesn't know that it has it, and yet is able to transmit the disease. So that is a particularly bad thing about this disease. And then, at the beginning of last year, our ex-president made all these remarks that this was just going to be another flu. So, typically in the United States, on a normal year, we have about 60,000 people that die from influenza or flu. We've had, in the first 12 months of COVID-19, more than 400,000 people. And this is with all the preventive measures that we took. So it's orders of magnitude more deadly than any influenza or flu that we have in a normal year. So what are the mitigation options? What can we do to prevent or to destroy the pathogen or the transmission? So if we have the two main modes, if we think from a mechanistic point of view, we have the so-called spitting mode and the so-called smoke mode. So what do we do for each one of these? Okay, on the left, you have the list of all the standard procedures that have been proposed and done in many places over the last year. And green means it's okay. Yellow means it's going to do some good, but not great. And red means it doesn't do anything. Okay, so for example, for the small droplets, for the smoke transmission, washing hands is not going to do anything for that. Okay, or for example, if you have maximization of fresh air in HVAC systems, for the large droplets that fall down ballistically, that doesn't do anything. Okay, so I've put together the list, but you can see we have UV here, we have the HVAC systems, and of course we have all the plexiglass shields and the like. Few pictures that we took from some of the smoke experiments that I did. And this is in the New York Eastern District Courts, federal courts. You can see here, this was a volunteer that actually was smoking, so it was easy to do this experiment. This is without mask, so you can see the viral matter being transmitted. And you can see that in this case, we have an HVAC situation that is very dangerous because the air is not going anywhere. Okay, so if you think of this as a jury bench, all the jurors that are on the right of this person are going to get all his exhalation. And the situation is not without danger, even if you wear a mask, because you can see here, this is a person that wears a mask, and you can see the leakage across the mask. So even if the leakage is small, if you think about a jury that is sitting there for 6 to 8 hours in one day, and you have this continuous waft of air exhaled from one person that is ill to all the other ones that are in that room, the probability of infection of the other people is very high. So that's why it's important to know how the flow is in these buildings. Okay, let's talk a little bit about the physics. So as far as air is concerned, the movement of air is well described by the Navier-Stokes equations for incompressible flow. I don't have to go into that here. I mean, this is very well known. But you may want to have some extra diagnostic equations, for example, the age of air. So the age of air is simply this equation here. So you start with an age of 0, or when it comes into the HVAC system, you put an A equals to 0. And then you can see that if you don't have any velocity, then A comma T is equal to 1. So it just increases with time. And then you put the advection term to just propagate it down, wherever it goes. Then you may have equations for pathogen concentrations. You may have several of these if you have several pathogens. And then you have the UV irradiation equations where you want to know how much UV light a particle or a bacterium or a virus has caught as it meanders through the room. As far as the particle motion, these are very small particles, so you can do a simple two-way coupling between the two, so you exchange mass, momentum, and energy between the two, but you assume that the particle is a cylinder, right? And it doesn't have a porous effect, it doesn't have a volume effect on the fluid around it. And you know, these terms here, the drag terms and the heat conduction terms, are obtained from empirical relationships like the ones shown here. Okay. As far as the numerics, we use standard finite elements. We typically use unstructured meshes, so we can do arbitrary geometries and adaptive refinement. We tend to concentrate on simple finite elements, just linear ones. We do an explicit advection because these are the time scales that we're interested in. We're trying to see where things move with the air. We try to use one-step schemes because we want to have, in some cases, moving grids and adaptive mesh refinement. And we use an implicit discretization for the pressure and the viscous terms. The results are independent of the time step at steady state. We use edge-based data structures. I mean, this is all very classic, so I don't have to go into great detail in this. And then for preconditioning, if it's an isotropic grid, we use diagonal preconditioning and line nets in case we have Navier-Stokes meshes. So this is the basic scheme. You can see it's a fractional step scheme. We first do an advective diffusive prediction, where we take into account the gradient of the pressure at the current time step, and then we correct the pressure with a Laplacian, and then we finally correct the velocity field. As far as the particle motion and temperature, you can see these are simple ordinary differential equations. They're non-linear, of course, but they're relatively easy, and we integrate them using a fourth order Runge-Kutta explicit scheme, and we trace the particles through the mesh using a vectorized near-neighbor search. As far as the UV radiation, the irradiation function depends on the distance and the angle, and typically diminishes, the radiation diminishes with the square of the radius. But you may have shading in complex rooms, so you need to do some kind of ray tracing for this. And what we do is we go from each element to the UV light. Okay, the assumption is that you're not trying to put people through UV light. Okay, that's a really bad idea. So you typically put the UV light in the top part of a room or in an HVAC duct, and you don't, so the shadowing doesn't change. So how do you do that? Well, you start at the Gauss point of an element, and you go back to the lights that you have. Typically, it's not more than, you know, half a dozen lights in a room. So this is a relatively simple thing to do at the beginning, and you can write the equation for a ray that is being traced from an origin, so from an input to an output in an element, by writing down the shape functions here. This is this vector psi. And so given an input location, you can get the output locations by looking at these differences in psi or in delta x. And delta x, of course, is the velocity or the ray, the unit ray vector times delta t. And so now you can get several delta t's for where the ray is going to go out of that element. And you take the shortest delta t, and that gives you the next element. And in that way, you trace your way through the element and you get there. There are several ways of making this faster. So you can, instead of doing for every element, for every lamp, you could do like a tree structure. So you can, as you go along the ray, you can sample all the elements that are in there, and then in that way you can save CPU time. But this is so fast that it doesn't matter. Okay, and here you can see a typical case where we have a lamp in the middle of the top of, so middle of the roof. And you can see all the shadowing here because of the door, or for this person here, you can see the shade of that person, and then also of the bed. So now, finally, if you want to do a realistic run, we try to couple computational fluid dynamics with computational crowd dynamics. So this would be the coupling scheme. So we compute the CFD with FE flow, so the flow field. And then we have for each grid point the temperature, the smoke, the toxic substances, the pathogens, whatever it is. Then we go from the 3D volume mesh to a surface mesh, which is the base mesh for the pedestrian simulation. that is fed into PedFlow, which is the pedestrian flow simulation code. And then so now we have for each pedestrian the position, the velocity, and from the 3D flow field, the temperature, the pathogens, the smoke, whatever else. Then we advance the pedestrians, and then that gives back to FFlow the position, the velocity, and the temperature or exhalation also of a pedestrian. Somebody sneezes, for example. So what is interesting is that by coupling this for the first time, you can have a detailed transmission simulation. This is the first time that this has been possible. Nobody has been able to do this before, because you needed the movement of the people, you needed to have the exhalation, the inhalation, and of course the 3D flow field was the part that was transmitting it between people. Okay, so how do you couple this? Well, there are several ways that you can couple the pedestrians to the flow field. We use an immerse approach. So we discretize the people either with a tetrahedral mesh or with spheres, depending on the type and how they move. And then we impose the velocity and temperature of the people to the CFD points that are covered by the person. And so it's a very simple approach. As far as the pedestrian motion, any of these pedestrian flow or crowd simulation models divide the movement of the pedestrians into a global movement, so a strategic or tactical objective. I want to be there in that amount of time. And then you have a local movement, which would be the operational. So do I have people in between? Do I have to evade geometric obstacles or whatever it is? And so that gives you sort of like a will force. I want to be there. I want to be now at this place. And then you have the local movement that has the collision avoidance and you know, all the local geometrical info. So it's basically Newton's law, and the modeling happens in the force here. So I presented this before, but so this is the code that we use. It's a mixture of agent-based and social force model. We have forces via a minimal set of well-defined parameters like relaxation times. So how quickly can I get to my final velocity that I want? That depends on the fitness, of course. The desired velocity and the pushiness. Or you can also call it distraction. Okay, so if I have a cell phone and I'm talking, I'm not watching, I just bump into other people. Okay, so you can call that pushiness or you can call that distraction. Okay. So we have local collision avoidance, and you have a background grid for the geometrical or spatial search, and also to define walls or other obstacles, you know, moving pathways, traffic lights, elevators, things like that. Okay. So here's a picture of this. This is the Atocha attack. We did the blast simulation, and then we did the evacuation for this. So you can see the people evacuating there. This is another view of the same thing. And this is another view from the top. Here's another view. This is 100,000 people. This is the big mosque in Medina. And this is an evacuation simulation. These are 100,000 people trying to get out of the mosque. And then finally, I have this one here, which I showed a couple of years ago here. So this was one of the designs for Mecca. You can see the Kaaba there in the middle. And this is a prayer cycle that is just starting. People are lining up in order to start the prayer. Okay, let's talk about some examples. As far as the physics and numerics, we do FFlow for the flow, PedFlow for the moving pedestrians. Flow initialization, we typically start with a quiescent flow at 20 degrees Celsius, unless we have, of course, HVAC systems on or something like that. The sneeze, we model as a spherical region of 5 centimeters that is near the mouth. We know from experiments that we have a peak of about 5 meters per second at the peak, that it takes, you know, a couple of tenths of a second to, so we put sort of a triangular function for this. And for the velocity, next to the velocity, we also have a peak in the temperature for all that mass of air that we are exhaling. Yeah, so it's 37 degrees typically. And so we have a peak that goes to 37 and then dies down. Particle initialization, we used 4 size groups, and we release them every 5 milliseconds for about 0.1 second. And of course, we paired this to the velocity that we had for the exhalation. So we took 5 meters per second, and we took 37 degrees Celsius for the particles. There are 3 different time scales. You will see the particles colored. Red will be the bigger ones, and then blue will be the smallest ones. They are colored logarithmically, so every one of them is in order of magnitude smaller than the previous one. And you will see that the big ones will fall in about 1 second. The other ones will have a slower drop, and then finally the smaller ones will just float through the air. I'll just say from the very beginning, HVAC systems, because we try to design them energy efficiently, are very good mixers and lead to very complex flow fields. Now, you can imagine why this is the case. If you had a very simple flow, if it's cold in this part of the room and the flow is very laminar, I never mix the flow. Okay, so the point of an HVAC system is to mix as much as possible so that we have a uniform temperature and a uniform situation in the room. Which, of course, if you think about pathogen transmission, is exactly what you don't want. So it's sort of bad. All right, so the first run was, of course, the panic run trying to get out of Argentina. You know, what is the worst situation when you fly? Where can you get most infected? In the security queue, of course, because everybody's nervous, everybody's pushing, and you're very close and you have counterflows of people. Okay? So this is a simulation here where you have, you know, the rows. These are not moving. You can see here the refinement of the mesh close to the mouth. And then you can see here one of them sneezing. He hits, of course, the big particles hit the person in front. You can see the smaller particles sort of floating there in a cloud and then moving upwards. And you can see also in the plane of symmetry here, the velocity, and then the velocity drifting upwards because of the temperature difference. This one here was interesting. This was the second run, sneezing in a hospital room. I had a colleague in math whose wife was a nurse in a Washington, D.C. hospital. And so we started talking to the management and, you know, no, I mean, HVAC systems are very expensive. We can't change them and blah, blah, blah. So this run was done. We asked her to draw for us a sketch of one of the rooms there. And so this is how it looks. You have a doctor or a nurse next to that bed, and then that patient sneezes by mistake. Okay, so he doesn't have the mask, boom. Okay, you can see the big particles drop, but the tiny ones now go everywhere in the room, given the air is coming in through this part here at the top, and there is some exit in the bathroom here and also some at the door. And what was interesting about this run is once this was shown to the management of that hospital, the HVAC system was changed in 3 days, magically. Why? Because the doctors refused to go in. No way, because they saw it was so dangerous. So they had a problem. Okay, this is the same thing, but now I'm using a UV lamp up here. And you can see the color refers to the irradiation, the amount of irradiation that these particles have. And if you put a fairly strong lamp, the red means that the particle has been deactivated. So we know how many microjoules we need per square centimeter in order to deactivate these viral matters. This was a sneezing in a classroom. This is a GMU classroom. It has 9 entries at the roof, 2 exits, and you can see it's a fairly turbulent flow field. This is just another view from the side. And you can see here the 9 exit entries at the top, a typical classroom, and then the 2 exits here at the back, also at the top. So again, you know, when you have a sneeze, the ballistic parts, you know, if you're more than 2 meters away, nobody gets that. But of course, you can see here, because of the inflow, you had this cloud going up, and then the inflow from the air conditioning pushed everything down and then spread it in the whole room. This is a classroom with the ceiling UV. Of course, you can imagine that a crisis like COVID, suddenly everybody's an expert in COVID, and everybody is you know, all the UV manufacturers, you know, had a great day. And so there were a lot of requests on doing runs and showing that this works. it actually doesn't work as well as advertised. But okay, so here you have 3 lamps. You can see the footprint of that lamp, and you can see here I've only kept the particles that are active. So using a UV and in this case a fairly strong UV actually helps. So you have a lot less active particles. This was a subway car. This was done in collaboration with the New York Times. They did all the modeling, they did all the research of the entry, the flow, the geometry, everything. And you can see the way it works is here's the exit, and then there is an air conditioning unit up here, and then the air is then pushed back into the car along these slits here in 2 counterflow fashions. So this is just the flow on the boundary. You can see here the cross section. Highly turbulent flow. You can see these entrances here that produce these vortices. And if you've ever been in a subway, you can feel this motion of the air. It's quite realistic. And then this is what happens when somebody sneezes, and he's sneezing towards the right. So of course, a lot of the viral matter goes there, but you can see that some viral matter also goes towards the left. So a very bad situation, really. This was one of the latest ones we did, also with the New York Times. This appeared in a very nice article that they did about 2 months ago. It's a Boeing 737-500. We know from previous influenza studies that typically you have 2 to 3 rows and seats around you where you could have transmission. This case had about 1 billion elements, about 2.5 million particles, was run for about 100,000 time steps on 8,000 calls in about 2 days. So this is the case here of the velocity, and I'm plotting the velocity in the middle and also at the height of the passengers, because that's where they inhale. And it's a very interesting system. You actually, the flow goes out through these holes, and then there is a pump underneath that captures that. Then it goes through a HEPA filter, and a large percentage, of course, goes back into the cabin after it goes through the HEPA filter. These are different locations where people sneeze. I've colored them according to different the location, and you can see that indeed 3 rows is what matters. Okay, so compared to a subway, or compared to a bus, or compared to a TSA queue, being in an airplane is much, much safer. Okay, and if you look at the age of air, you can see here that the air that the passengers see or that they inhale is less than a minute old. Yeah, the air conditioning system recycles the air every two minutes. And this is what the aircraft manufacturers actually advertise, and it turns out to be right. Finally, this sneezing in a narrow corridor. Now we couple with pedestrians, and this is, let's say, the first time that you can do a detailed transmission model. You can see here, this is the same view just from 2 sides. Yeah, so it's the same case. And you can see here the flow field. You can see how the pedestrians influence the flow field and make this massively turbulent on a large scale. And now you have somebody sneezing, and you can see how the counterflow part receives everything and inhales it. Now you can do the same thing by looking at the viral matter. So I'm now solving a concentration equation, and you can see here the concentration of the viral matter and how it is transmitted, or moved around. So it's not just the people behind me that get it, or in front of me, but mostly the people on the other side in counterflow. So this was also something very important that we did for the US courts when you do protocols, so that you don't have counterflows in corridors, so that everybody's moving in the same direction. And then this is a simplified model. So if you cannot afford, or if you don't have the information for a complete flow field, you can use a simplified model for the flow field. So in this case, we have a simple diffusion equation, assuming we have bad ventilation. You can pre-store the motion of the pedestrians, and then you can do a lot of statistical runs. And so here's a case. This is a train station in Germany, subway station. And I've colored the pedestrians. Blue are the ones that are not infected. Then you have the green ones, these are the ones that come into the station infected. And then the red ones are the ones that have been infected by coming in contact with them. And so you see, well, this is a little bit hard to see, but anybody who's interested, I can send this video. So basically you see little puffs of viral matter, and then everybody that walks through that viral matter, if he's inhaling at that point, and if he inhales strong enough and a sufficient amount, then it's considered to be infected. And so you can do these statistics here with different probabilities and the number of people that are getting into the station that are infected, and contact they have with others and so on. And so you can do a lot of these runs very quickly. So that was sort of elucidating or trying to understand how transmission works and trying to simulate that. Then there is the part of reaching out, or let's say the educational part. And so I've had a couple of interviews with NBC. This is the Today Show. It reaches about 10 million people. And there were two interviews. I just want to show one of them from the last one. Let's see if it plays.
We're back at day 12. We've got our reopening America series rolling on, and more businesses like restaurants and theater.
Let me just move ahead a little bit. Oops, sorry. Oops. Let's see if I can.
Airflow. Experts use this ventilation smoke device. All you do is crack these two parts and then squeeze out a puff of smoke. That simulates what happens when a person exhales. If the smoke doesn't move around too much like this, it could be a problem. But watch what happens when I have an open window nearby. The smoke dissipates.
Okay, so this is this lady, and she goes into supermarkets. She goes into all sorts.
You can see it's not so great, which is why rideshare companies ask people to put their windows down. That really helps with the airflow. Watch this. Gone. Okay, let's give it a try here in the hardware store. The smoke didn't seem to move at all. I can definitely still see wisps of smoke. Let's compare what happened inside where the smoke didn't really.
This is that. So this is the restaurant. And then this one here.
What happens inside an empty movie theater. So it's moving, but the crowd isn't really dissipating very quickly at all. We showed our videos to Professor Lohner. He runs the Center for Computational Fluid Dynamics at George Mason University. He uses the smoke tube in his studies. He worked with us last summer to show us what happens inside a classroom with poor circulation. What did you think about what we found?
It shows very clearly that there are certain areas that are problematic.
Okay, but you get the idea. Okay. So finally, what do we do after the crisis? Okay. We will have a lot of sensors put into buildings, and there's some talk that we're going to get sensors soon for pathogens. So we will be able to detect COVID and possibly other future pathogens. So there's a lot of startups working on this. There's a lot of emphasis also from the NIH and from the CDC on this. So the question is, where do you place these sensors? How many of them and where? So we did a first run at this. So the idea is to run many scenarios, place many sensors, and then pick out the best locations for the sensors. I want to show one example. So we have a hospital room here. We have 3 inflow vents, and we have the patient. And we're going to assume that through one of these vents, we may have some pathogen coming in. And can we detect it? Okay, so this would be the average velocity here. We have the 3 vents. And so we assume we have contaminants coming in for 60 seconds. We have a viral production from the patient for 10 seconds. And then we run it for 5 minutes and see what the sensors would see at the wall. Okay, so this is the age of air after 5 minutes. You can see there are some regions here that have recirculated and have a considerable amount of age there. And so these are the max values that the walls see based on the pathogens of vent number 1. This would be vent number 2, and this would be vent number 3. You can see vent number 3, there's almost no, so if you place some sensor on this wall here, that sensor wouldn't measure anything. And then finally, there's the part of the patient. You can see this is a highly recirculating flow, so this viral matter stays here for a very long time, which is what we saw before in that video. So if we take every finite element point on the boundary, or let's say every 10th of them, and then we assume that that could be a sensor location, then if we have, we can now do the statistics of, how many points do we have that measure no cases? Well, all of them have measured at least one case. But out of the 4, there are some that only measured case number 1 or some other case. So now what we do is we take the points that measure the most cases and we try to cover all the cases with a minimum amount of measuring points. Okay, so it turns out that these are the 2 locations that come out. Okay, these are the ones that measured the highest values and measured all of the 4 cases. And you can see this makes sense. This one is close to the pedestrian at the wall, and this one is at the top of the roof, where you can also put a sensor and is, takes care of the 3 exhausts. Okay, so let me come to an end. I've summarized the mechanical characteristics of virus contaminants and the transmission via droplets and aerosols. I've made emphasis on high-fidelity physics, so the PDEs, the ODEs, some appropriate numerical methods for them. Then the linkage of CFD and CCD, computational crowd dynamics, and that for the first time allows a quantitative pathogen transmission simulation. And then I showed you some examples and finally finished with optimal placement of sensors. So where do we go from here? Well, there's a lot of work that has to be done. First of all, we have to improve the boundary condition for HVAC systems. We think that this is one of the weakest points right now. If you look at a typical HVAC exit, you can see they have vanes, so you don't know how the air is coming out precisely. You don't know what the mixing is there, what the turbulent scales are. And we would like also to have, for statistics or sensitivities, increase the realism of all the inputs that we have. Okay, so the number of people, how they walk, the HVAC systems, the actual weather, humidity, temperature, things like that. And then combine this with some kind of a robust experimental campaign. So we need to have good quantitative results to compare and validate what we have. Otherwise, it's just pictures. And then, of course, it's important to link to the NIH or to the CDC or the World Health Organization for clinical relevance. So can we please get more information on what the critical viral loads are? They may be different for different age groups. They may be different for different ethnicities, for different sexes, but we need to know those numbers because otherwise we cannot get a good transmission model. And then, of course, streamline this and field it as much as possible. Okay, thank you for your attention.
Okay, thank you very much, Reynald, for this presentation. It was very nice. I think we have time for some questions. If anybody wants to ask, I think Alfredo Portone just raised a hand. Go ahead, Alfredo.
Thank you very much for the presentation. Very, very interesting. I have 2 questions, maybe also a comment. It seems to me that there is some cross-field interest here if we link this type of transport diffusion equation to what is done in the field of isotopes, contamination, and transport with radioactive dusts and such like in the nuclear fields. I mean, dust is particulates that flows and in the air, and it also has a time where the isotopes decay, so somehow is also similar to this type of problem. So is there any cross field that we can exploit here?
Absolutely. I think, in fact, we had, or we still have in our CFD center, a large group working on dispersion of contaminants in the urban scale. And, a dirty bomb is a typical case, and that would be the, it's also isotopes, okay? And, if you are in Washington, D.C., that is on the radar, okay? So that's some of the things that we do over there. Yeah.
Excellent. Okay. I would be interested in following up this. Maybe I can contact you then. Okay. Thank you. Very nice.
Thank you. Is there any other question here in the room or outside? Any comment?
My question was, each of those particles represents many particles, right?
That's correct.
And my question is it not too big? I mean, the amount of viruses that were needed to infect one person, is that many of those particles, or just one of those particles, or less than one of those particles?
No. You try to have a sufficient amount. And the thing that happens is that for the smaller particles, if you look at the amount of viral matter that can be in the smaller particles, it becomes very small very quick. Okay, so yes, there are a lot of small particles out there, but the amount of viral matter is also very small.
Okay, so typically in one of those particles, simulated particles,
yeah,
there will be what, one virus? Or?
Yeah, or 0.1 or something. Okay. That depends on the diameter and the number of particles that it represents in real life. Yes. So the idea is that you have a sufficient number of particles per element so that if there is a person there to inhale, you have at least the statistics right. Now, it's of course impossible to simulate every particle because the number is just so astronomical. Yeah, so you do this compromise that every particle represents many particles. The other option, of course, is what I showed for the cross streams, that you solve an actual advection diffusion equation for that viral matter.
For the concentration.
Yeah, for the concentration. And yeah, you can do both things. I like to see the particles myself, but that's a different matter. Yeah, it reminds me of smoke. Okay, just yeah.
Okay, thank you. Is there any other question online or any comment? If there are no more questions, then let's thank.
Oh, wait.
Yeah, sorry.
What do you think about octane meshes?
Octane meshes?
Yes, because we are using embedded, you are using...
Yeah, that's fine, we use it too.
Because it should be much easier to do all this kind of continuous remeshing and so on. Even CRT. So
okay,
like
so
faster than constructed meshes.
No, I don't think you would see any difference in speed whether you use a structured or unstructured mesh here for what we use. Okay, the main reason we use unstructured meshes is because we want to have the geometry of the building right. Okay, so if we have architecturally interesting buildings, we will have curvature, we will have HVAC entry points that may be in some funny place. If you have you can do that embedded, of course. You can apply the boundary conditions as you want. That's fine. As far as the people moving through it, we use an immersed technique. So we apply a boundary condition at a point, so it doesn't matter if the point is structured or unstructured. The search is independent of whether the points are structured or unstructured. Because all what you have to find is, if I have a mesh of tetrahedra or a couple of spheres that represent a person or ellipses, I have to find which points in my 3D mesh are covered by that person. So that search is independent on whether I have a mesh or not, because I have to find the points.
The search is fine. I was thinking about the necessity of a concentration of mesh for resolution of the CFD. Or
Yeah. For example, we typically tend to put much finer meshes at the exits of the HVAC system, something like that. Yeah, sure. But whether you use Octree or straight unstructured, you still have to define where you want to have the fine mesh.
We're just thinking that it's much faster to structure mesh, and they should be faster than remeshing completely. It's not refinement. In your case, it's remeshing.
Yeah, but I don't know. I mean,
if you couple this with embedded, with immersed.
Yeah. No, I
think that is the best solution.
It is a very good solution, and we use it also for a lot of the runs that we do. For example, for every run that I did here, I did not use the embedded approach because I had a good watertight geometry.
Okay.
Yeah, and in that case, the advantage of, say, what we find is that an embedded mesh, you need a mesh of size h/2 compared to a body-fitted mesh to get the same accuracy. So you know, in 3D, H/2 is a factor of 8, or you know, 4 if it's local. So there are benefits of having body-fitted meshes. So if you get a nice watertight geometry, it makes no difference. And you know, generating that billion-element mesh on 16 cores, shared memory, I don't know, 20 minutes, maybe less. So it's not an issue. The run takes 48 hours. So if I spend another 20 minutes generating the mesh, it doesn't matter.
If you're sure that you succeed in generating the mesh,
let's see. Okay, but you can be sure that you succeed in generating the mesh if you generate a good surface mesh. And we have, I mean, if you have let's say, in our case, we know that if we are able to generate the surface mesh, we're able to generate the volume mesh. Yeah, that is not an issue. If the grid generator fails, it usually fails because the surface mesh is either crossed or bad or has some, you know, holes or whatever. Okay, but that's something you can detect, and that's something you can tell the user before you generate your 3D mesh. So it's a very quick thing, because all you're doing is generating a surface mesh, and then you're telling the user, things are crossing, or things are missing, or things are not closing here. So let's say that the volume part is time. I mean, the surface mesh for that 757 may have taken, what, 2 seconds to generate. And then, you know, it takes 20 minutes to generate the billion elements.
thank you.
Okay, thank you, Owen. Is there any other comment or question? If not, let's thank Professor Reynolds again for the seminar. And see you in the next session of the seminar course, which is tomorrow. Okay? See you. Bye-bye.
Impressive as usual.